4 talks today. So the first one is Robert Aufart from Universidad de Chile, and he will be talking about counting polarizations. William Barrett.
Thank you very much. Thank you for the organizers for the invitation to give this talk. It's also an honor to be number one, although I saw that it was by alphabetical order, so it's nothing special, but thanks anyway for this privilege. Today I want to talk about, I'm going to start with one problem, and I'm going to make my way to a completely different problem. So I hope it'll make sense. So this is joint work with Rubí Rodriguez and Ángel Caroca. And one of the problem I want to start off talking about is a problem that I have a kind of a love-hate relationship with. In the sense that, so I'd like to talk about why I have a kind of a hate relationship, maybe not hate, that's a little strong, but start off why I have had frustration with this problem. Number one is that I've never been able to make any progress on this problem whatsoever, even though I've tried. And I've failed spectacularly at trying to work on this problem. So for example, a couple years ago, I realized, okay, so the problem is if there exist completely decomposable Jacobians of arbitrarily large genus, dimension. Okay, so if we can find Jacobians, we can think over the complex numbers if you want. If we can find arbitrarily large Jacobians that split isogenously as the product of elliptic curves. And so this is a question that Egedal and Serre made in an article in the 90s. In their record, they found up to genus 1,297. Okay, and they filled in, they found several genera in between, but they didn't find all of them. And so lots of mathematicians, many here in Chile as well, have been completing genre, finding completely decomposable Jacobians of different genre between 1 and 1297, okay? And so I thought that I'd have my try at this, and in 2017, I realized that if we have an abelian variety, and there's a finite group of automorphisms such that the quotient is projective space, then you have automatically that the abelian variety is isogenous to a self-product of elliptic curves. Okay, I thought this was pretty cool. And so I thought, what happens if maybe we can characterize Jacobians that have a smooth quotient, or a quotient that's projective space. So with Giancarlo Lucchini, we worked on this, and 5 papers later, we were able to almost reach 1297, and we were able to show that the biggest genus where there's a smooth quotient of a Jacobian is genus 3. Okay, so it was a complete failure. But, so that's kind of why I've had frustration with this problem. I've never been able to do anything with regards to this. But my love relationship with this problem is that every time I've tried to attack it, interesting math comes out and I go in a completely new direction. And so, like, for example, with smooth quotients, we were able to write 5 articles, and it was a really interesting area, but it didn't have anything to do with this problem. Okay, so I want you to keep this problem in mind, because this problem is going to be, once again, it's going to be the motivation for what I'm going to talk about, but once again, I have nothing to say about this problem in the end. Okay, we're going to go in a new direction. Okay, so let's put this aside for a second, and I want to talk about something else. So we're going to start off with an abelian variety, okay, over an algebraically closed field of characteristic 0. You can think of the complex numbers if you want. A polarization on A is just going to be an ample line bundle and defined up to translation. Okay, so if you want, maybe it would be better to think of the first Chern class of this line bundle, but let's just think of it as a line bundle. And it's going to be a principal polarization. Principal polarization if H0 is 1. Okay, so that's 1 up to multiplication by scalar has 1 global section. Okay, and so we're going to define. Let's define AG. It's going to be pairs of abelian varieties with principal polarizations. So L is a principal polarization. Mod isomorphism, where we're going to say that two are isomorphic if there's an isomorphism between them that sends one of the line bundles to the other. So this is a quasi-projective variety, dimension G times G minus 1/2, or G plus 1/2. It's the dimension of symmetric matrices of G times G. And we're going to define, if we have A again, we're going to define PP of A. Let's just do 1P. This is what the notation that Lange uses. This is going to be the set of principal polarizations mod the action of the automorphism group. Okay, that includes translations or ones that fix the origin. And PP, small p of A, is going to be the number of elements here. Okay? So, by theorem of Narasimhan and Nori, this is finite. Okay, so if you want to think of this over the complex numbers, a complex torus that has a principal polarization, the complex torus is going to appear a finite number of times here in AG as the first coordinate. Okay, and so this number PP of A is going to denote how many times that complex torus appears in AG. Okay, so if it has two principal polarizations, then there's going to be an AL1 and an AL2 here in AG, for example. Okay. Okay. So if we have our principal polarization, then we have a function that goes from A to the dual of A. That takes X, we're going to translate L by X, and then tensor with L to -1. By the theorem of the square, this is going to be a group homomorphism. Okay. And actually, so if L is just a polarization, this is actually an isogeny. And if L is a principal polarization, then this is actually an isomorphism. Okay. So for a principally polarized abelian variety, then A is always isomorphic to its dual via the principal polarization. And principal polarizations are so important because they appear, of course, as, for example, Jacobians of curves are naturally principally polarized abelian varieties. So that's why, also prim varieties, and there are a bunch of different sub-varieties of this space that are very interesting, geometrically speaking. Okay, so now if we have this, let's consider the following map. So it's going to be called the Rosati involution. This is going to take an endomorphism. So the endomorphisms, they're going to fix 0. We're going to send this to, so we can think of, we can have a little square here. Let's say we have A dual, this is phi L. Here we have F. Here we have phi L again. And then by pullback of line bundles, then we're going to have this F dual, right? So what we're going to do is we're going to send this to phi L to -1, F dual, phi L. Okay? In general, if we just have a polarization, we also have the same map, but we're going to have to tensor this by Q. Okay, so we're going to have Q endomorphisms because this is just going to be an isogeny, and so the inverse exists formally, but not as an actual homomorphism. Okay, but we're talking about principal polarization, so that's enough for now. And so this is actually an involution of this algebra. Okay, so we have that, I'm going to write it like this. This is F, and it's also linear. Okay, so we have an involution, and so we have something interesting with this involution. Huh? It's a dagger. I don't know how to draw that well, but some people use prime, but I think a dagger's a lot cooler for, so yeah, I like the dagger. Okay. Okay, so we have the following. So actually, this map up here, phi L, I can define that not only for a polarization, but I can define it for any line bundle. Okay, and actually, phi, it only depends on the numerical class of the line bundle. Okay, so I can actually define that for class in the noun severity group. Okay, so we can define a map that goes from NS of A to the homomorphism group, and we're going to do the following. We're going to take an alpha, and we're going to send this to phi A to the -1, composed with phi of alpha. Okay, so this again, this is just going to be the class of some line bundle. I don't know, L tilde, and this is just going to be phi of L tilde, and that's well defined. Okay, it's not hard to prove. So this is going to give us a homomorphism, a group homomorphism. Note that here we're seeing the endomorphism of A as a group with a sum. Okay, we're not looking at the ring structure where we have composition as well. Okay, well we're just looking at the group structure as with addition. Okay, so this is a group homomorphism, and it's actually injective. And we have the following. So the noun severity group is isomorphic to the symmetric endomorphisms, which are just those fixed by the dagger, right? The Rosati involution. Okay, so this is injective, and the image is exactly the eigenspace associated to 1. Okay, and again, if we wanted to do this, okay, so notice first of all that the Rosati involution depends on the polarization I'm choosing. Okay, if I choose a different polarization, I would a priori get a different involution. And so this isomorphism also depends on the polarization I'm starting off with. Now, if I start off with a non-principal polarization, I just start off with any, then again, I'd have to tensor all this with Q. I'd have to tensor this with Q as well, tensor this with Q. Everything works out fine, and that it works in many situations. So, I mean, it's helpful to work with this group in many situations. But here, for a principal polarization, all this is well defined. Okay, so you might ask then, what do the principal polarizations in here go to over here? Okay, so first of all, we notice that if I have a principal polarization, then this, okay, so this phi L, this is an isomorphism with the dual, and phi of alpha, if alpha is a principal polarization, this is also an isomorphism. So this is going to be an automorphism of A, okay? So it's going to be a symmetric automorphism. If we start off with a principal polarization, it's going to give us a symmetric automorphism. And also the fact that it's a polarization means that it has certain positivity properties. And what we're actually going to have is that alpha, if alpha is a principal polarization, whoops, then this endomorphism, this automorphism, its characteristic polynomial, its roots are going to be totally positive, and so they're going to be greater than 0. Okay, so this is something as like a finite. I have a certain amount of time to write here before I can go to the next one. Okay, so this is Lange in I think it's 87. So show that there's a bijection between principal polarizations on A and symmetric automorphisms of A, okay, that are totally positive, mod a certain relation, which that's going to be the relation basically associated to modding out by the automorphism group here. Okay, so again, so let me write this down. This is going to be F in the automorphism group such that it's fixed by Rosati, and the characteristic polynomial of f has positive roots. Greater than 0. Okay? And f is going to be equivalent to g if and only if there exists, for example, sigma, the automorphism group of A, such that, let's say that fixes 0. I forgot about translations a long time ago. So every time I speak of an automorphism, I'm thinking of one that fixes 0, such that, so G is going to be with a sigma Rosati F sigma. Okay, that's the relation. So basically, this is just, this translation here is basically going through this isomorphism, realizing where principal polarization ends up over here, and then translating the action of pullback by an automorphism to an action here, and we get that. Okay, so this is what Lange did in 87. And then he proceeds to compute several interesting examples in this article. He published this in Duke. Okay. Now, a little bit further on, in I think it was 2005, Lange studied how basically the set of principal polarizations on a product of elliptic curves. Okay. Here there is. Let's see, where did I define it? Oh, sorry, this is PA. This is right here. It's mod the automorphism group. Yeah. Okay. So, Lange, and I think this is 2005, he wrote an article basically using this characterization to study how many principal polarizations could lie on a product of elliptic curves. Okay? Now, think back to Egedal and Serre. We're thinking about principal polarizations on products of elliptic curves. And so he basically proves the following. For example, if, let's say, E without complex multiplication, so this is going to be the number of, let's see, unimodular, integral, quadratic forms, mod equivalence. Okay, equivalence of quadratic forms. Which is, this number is interesting in number 3. And so, for example, he shows that, so this is 1 if G is less than or equal to 7. So for example, I could say if you have E without complex multiplication, E to the 6 only appears one time in the moduli space. There's one principal polarization. But then he proves, for example, I think if I remember correctly, that E to the 8 is equal to 2. Okay. I think I might just go to the top board. Let's see. Okay, but then, for example, he shows that E to the 32 is greater than or equal to 80 million. Okay. So, for example, E to the 32, as a torus, if you want, the actual variety appears more than 80 million times as a point in the moduli space. Okay, pretty cool. So this got me to thinking, what happens if we have a Jacobian that's isomorphic to a self-product of elliptic curves, for example? If E to the 32 is a Jacobian, well, Jacobian should have many principal polarizations, okay? Or another way of thinking of it, how many of the principal polarizations on this make it a Jacobian, for example? There might be even more than one. And actually, there are many examples where, in small genus usually, genus 2, genus 3, where you can have Jacobians with more than one principal polarization, and with more than several of these principal polarizations actually make it into a Jacobian in different ways. Okay, so basically you can have two non-isomorphic curves that have isomorphic Jacobians. Okay, and for example, you could ask up to what extent the complex torus determines certain geometric properties of your curve, and it seems like it's not that much. So like, for example, you can have a curve that's non-hyperelliptic, You can have another curve that's hyperelliptic, and they have isomorphic Jacobians as complex tori. Okay? So how to distinguish between different principal polarizations, it's not that clear. Okay? And actually to ask if a principal polarization gives you a Jacobian, it's a very hard question. That's the Schottky problem, which is a problem that is very interesting, a problem I like very much, but it's very hard. Okay, so another thing about this that he shows. So for example, if we have, let's say we have E1 and E2 with a minimal isogeny of degree D. Yes, I'm not saying this right. Let's say we have two isogynous elliptic curves, and the smallest degree of an isogeny between them is D. Okay? Then he shows, for example, that this number goes to infinity when D goes to infinity. So we can have abelian surfaces with an arbitrarily large amount of principal polarizations. Okay? Now, what does that mean in terms of this function? For example, if I think of PP goes from AG to the natural numbers, it means, for example, that this function is, it's not, for example, semi-continuous in any way, which is something that we always want. If we have functions defined homogeneous spaces, we always want to know if they're upper semi-continuous or something. But this is a very strange function. Okay? The fact that this goes to infinity says that this isn't upper semi-continuous. Now, what we can prove, since we have this nice characterization here by Lange, which I already erased, that we know that the endomorphism ring is constant for if we have a family of abelian varieties, then the endomorphism ring is constant for a very general element. Okay, and so basically the endomorphism ring gives us, we can obtain this function from the endomorphism ring. Okay, and so what we can say is that this function is constant for a very general element on a family, whatever that means. Okay, we can be more specific for certain families, but in a certain way, if we have a subvariety, a positive dimensional subvariety here, then there's going to be a certain constant that most elements in some sense take. Okay? Now there are going to be other points where that number could go down or could go up. Okay? But there's going to be a certain generic number that most will take on. Okay. Yeah.
These two elliptic curves, any elliptic curves?
Yeah. Yeah, so, okay, so what does it mean when D goes to infinity? It's again, I'm not saying it correctly. We can take, like, for example, E1, we can, like, for example, I can take, I get, let's see, E1 is this, I could take E2 to be, is that right, or is this, maybe it should be E1, and this was E2. Okay, and so this naturally, well, I mean, I went out both ways, but this naturally goes to that because this lattice is included in that one, and it's of degree D. Okay, so this would be an example. And so when D goes to infinity, the product of these two is they're gonna be arbitrarily large, an arbitrarily large number of principal polarizations when D goes to infinity. So the question is then the following: how many? What happens if we have a Jacobian? How many principal polarizations can it have? Okay, and so up until now, most ways of attacking the Ekadal-Serre problem of wondering when a Jacobian is isomorphic or isogynous to a product of elliptic curves, most of the strategies involve using automorphisms and decomposing the abelian variety and seeing if we can get a decomposition with factors that are as small as possible. Okay, and that's even the strategy that Ekadal and Serre used. And so I wondered, so what happens if we have a Jacobian that has a non-trivial automorphism group and then see how many principal polarizations it can have, okay? So recall that I think it's for G greater than or equal to 4, the singular locus of AG is going to be principal polarized abelian varieties such that the automorphism group is not plus or minus 1, plus or minus the identity. Okay? And so what I mean by this is those automorphisms that fix 0 and such that upon pulling back L, it gives numerically equivalent to L. Okay? And so the question that I reduced kind of this study to is the following. Given a positive dimensional irreducible component of the singular locus, what is PP of A for a very general element AL in, let's see, component Z of Z? Okay, so when I first asked this question, usually when you think of something very general and you want a number associated to it, usually that number is going to be somewhat trivial. Okay, so like for example, if you ask what's the Picard number of a very general, I don't know, abelian variety, it's 1. What about a Jacobian? 1. What about a hyperelliptic curve? I think it's also 1. And so I thought, well, I mean, it makes sense for this number to be 1, probably, okay? But that's what's surprising. It's not always the case. Okay, so I want to explain this really quick. Okay, about 10 minutes. Okay, so the details of what I'm going to say, I'm going to leave out the details. The details are things that we're still working on. So I'm going to say a couple of things that aren't quite true, but or not quite specific, I guess. Okay, so fact. Maybe fact. In many cases, the very general element of Z has endomorphism ring Z, and we add a p-through unity. Okay? Why is that? Well, it was shown, I guess, at the beginning of 2000s by let's see, Victor Gonzalez, Alexi Garcia Zamora, and Jose Maria Muñoz Porras, that they basically describe what the irreducible components of the singular locus of AG are. And so basically, all the irreducible components are, they have, are abelian varieties that have an automorphism of order P with some other information, okay? And so basically, we know that the very general element is going to have some automorphism of order P, and so in many cases, the endomorphism algebra is going to be Z, and we add this automorphism of order P, okay? Now, the work in progress that we're doing is analyzing this right here. In what cases? In many cases, we do have that. Now, exactly what cases do we have that? And that's, it's quite technical and we've had to go into many very particular cases, okay? But there are many cases, and I dare say maybe the general case is this, okay? One thing that we were able to, for example, remove is what happens if this automorphism of order P acts with, if it has infinitely many fixed points, for example. We were able to throw away that case. And so we basically reduced to the case when the automorphism only has finitely many fixed points. And so we have to go to different cases, and we're still working on it, okay? But for the purpose of this talk, I'm just going to say in many cases. Yeah.
That's right. When you say many cases is when you consider the different this will perform.
Yes, yes. I'm going to leave it kind of blurry. It's, yeah, so most of the components should satisfy that. There are certain components that we think we can describe where that isn't the case. And those cases where we don't have this, we think we can still work on this problem and say exactly how many principal polarizations there are.
But you know components that they don't have this.
Yes, there are components. For example, take principal polars to be divided with an automorphism of order P and multiply that, take that times an elliptic curve, for example. Then you're going to have a general elliptic curve. Then you're going to have Z, for example, in one factor, and then you're going to have the endomorphism ring in the other. Now, this other factor doesn't bother me. That's the thing where I can reduce it to the study of this factor where we do have that, right? So in very general terms, I can basically reduce to this case modulo a couple of cases that I'm not going to go into. Okay, now what happens here? So when we have this, remember that Lange showed basically how to, from the endomorphism ring, basically from the automorphisms, we can figure out how many principal polarizations it should have. So here we're going to have that, in this case, we have that the symmetric endomorphisms are just going to be, so here the Rosati involution, you can show that it's just complex conjugation, okay? So the symmetric automorphisms, the symmetric endomorphisms, so just be, we take a P through, we just take the real elements here. What about the symmetric automorphisms? Well, this is just going to be, yeah, I'm going to cheat the invertible elements there. And this is actually a very interesting group. And then the totally positive ones, those whose characteristic polynomial have roots that are positive, we're just going to call it, let's call this UP plus, okay? Okay, U from unit and plus from the positive units there. Okay, and then, so we're going to have the following, UP squared, okay, so this, I'm going to call this UP right here. Okay, so all the squares, you can show that any square is going to be totally positive, so this is going to be a subgroup here of UP plus, and we're going to have fact, so if then the morphism ring of A is Z, and we add ZP, then the number of principal polarizations on A is actually the order of this group, UP plus mod UP squared. Okay, so this is an interesting group, the order of this group. This is actually, for example, you can take this is the narrow class number divided by the class number, for example, of the cyclotomic extension. And so I asked Eduardo Friedman about this group, if he knew anything about it. He asked Dummett about this group. Dummett thought it was very interesting, and he thought it was interesting that this was associated to principal polarizations in a certain moduli space. So he, Dummett, along with a colleague, wrote an article, which basically one of the corollaries of his article, this is from 2019, proved that this number is, in some sense, many cases 1, but there are infinitely many primes where this isn't 1. Where this is, it's always a power of 2. Okay, so for example, if P is equal to, the first one where this isn't 1 is P equal to 29. And here we're going to have that PP of A is going to be equal to 8. Okay? Then let's see, what are the other primes here? For example, if P is equal to, so in the other ones, the first list of primes where this isn't equal to 1 is, so then we have 113, then 197, then 239, then 277, and then 311. Okay, so for this prime we have also 8 principal polarizations. We have 8 here and 8 here. For this one we have 4, and for this one we have 1024. Okay. Okay, so now the question is, are there really abelian varieties with these primes that satisfy this? Okay, and the answer is yes. We can take an example by citing. So for example, if we take y to the p equals f of x, degree of f is n greater than or equal to 5, and we want the Galois group of f to be either an or Sn. Okay, then the genus, let's call it C. The genus of C is going to be equal to, p minus 1, n minus 1 halves. If p does not divide n, and it's p minus 1, n minus 2 halves if p divides n. And so, for example, and what he proves in each of these cases, for this curve, is that the endomorphism algebra of the Jacobian of this curve is actually z, and we add zp. This is for any prime. So, for example, I can take any of these primes, and what I get is not only a Jacobian, but I also know that this Jacobian lies in an irreducible component where the very general element is going to have this amount of principal polarizations, and so on. Okay, so for example, this is the last thing I'll write. So for example, if we put p equals 29, n equals 5, then we're going to have g equals 56. And so basically there's a component in the singular locus of A56, a positive dimensional component, such that the very general element here is going to have 8 principal polarizations. So each member of this component is going to each one have 8. And then, so for example, I wanted to do the big one. P equals 311. Let's do n equals 5 again. And here we're also going to get g equals 620. So for example, there's a component, an irreducible component in the singular locus of A620, where the very generic element is going to have 1024 principal polarizations. Okay? Which is, it's strange. It's not something I was expecting. And the other thing that I find interesting, which is also, I want to study, is the fact that this actually, this forms a group. So the principal polarizations are in bijection with a group, an abelian group here. And so I want to know if maybe there's some kind of group action on these components that we could study. Now, of course, this identification between the principal polarizations and this group depends on a fixed polarization. So I don't know if maybe fixing a polarization on one element, then we get a group action, for example, on this whole component. I don't know. There are lots of questions that we're still working on. But what we'd like to get is an answer of the type, given I don't know, all irreducible components of the singular locus for G up to a certain number, PP is equal to 1, and for certain G's and for these components, then we have a different number, for example. Basically, give a whole characterization. That's what we're working on right now. So it's a work in progress. We have a lot to do, but I think it's an interesting problem, and I forgot about Eke-Gaussier a long way back. I'll leave it at that. Thanks.
Do you know if this function is bounded? Cardinality of P over.
It's not bounded depending on G at least. No, even for abelian surfaces, you can, the case of E1 times E2. Oh, this function, sorry. That's a good question. No, it's not bounded. It's not bounded, yeah. Sorry, that's one of the corollaries of the article. It's not bounded. I could give an example. I'd have to think about it a second. But the thing is the fact that it seems like almost anything could happen. It's not exactly clear what happens. The thing is, since this depends, the number of principal polarizations depends on the automorphism group, which is, in a certain sense, somewhat stable, I guess, in families. But then you mod out by, so you have these symmetric automorphisms that are totally positive, then you mod out by the automorphism group. So when you mod out, then it's unclear exactly what happens when you take a limit. I'm pretty sure I could think of an example for you where the number drops. That shouldn't be a problem. That's a great question. That's a very good question. No, I don't know. I know. I think there are many cases where they do. I think in most cases they should be in the same component. Now it's not clear if they always should or not. On the actual component. Yeah, that's kind of the semi-conjecture. I don't want to conjecture yet because I don't understand it well enough yet. And then I have another interesting question, which is, I think would be very hard, is given these, for example, even in the case of the simple of z with a pth root, which ones correspond to Jacobians? I think that would be a very interesting question, but I think it would be very difficult.
You can say something about taking the case of Wayne-Bannon with Sasadicons and or
I don't know. You want to know about the moduli space of principal polars of polarized Abelian variables with Shadji constant equal to 1? I don't know. I'm not sure. Thanks. Sí. ¿Sabe para la próxima charla usar de arriba, no? Ah.
change the title. See? Yeah. Okay. Thank you very much for the invitation. It's really a pleasure to give a talk here. I was an undergrad student here, my home. Okay, so let me grab my notes. So the first thing is that this is all joined with Pietro Veri, Lord Flapan, and Brandon Williams. And so let me set up a bit the stage. So, I mean, I guess to this audience, somehow I don't have to justify the fact that if you have a variety, maybe also a disclaimer, this is all over the complex numbers. Yeah, algebraically close characteristics. Then the divisor geometry, right? So the divisor geometry governs a lot of the geometry of the variety, right? It tells us line bundles, how I can put it inside the projective space. It tells me a lot about the birational models, and so on and so forth, right? So yeah. So here there is a lot that one can say, and this is, I'm being vague on purpose. So for the moment, so projective embeddings, equations for my varieties. It tells me things about the birational geometry, and so on. And when X is a moduli space, right, it's a variety whose points parameterize a given class of varieties. So when this is a moduli space, right, so a special class of divisors that we want to study that show up naturally are what are called modular divisors, meaning divisors defined by a codimension 1 condition of the objects that this moduli space parameterized, right? So modular divisors. And then you can ask the same questions. Which ones are effective? Which ones are in sections? What are the relations between the sections? Blah, blah, blah. Yeah? So let me maybe give an example. So for instance, MG bar, right? Moduli space of stable curves of genus G. Right, so natural modular divisors are, for instance, boundary divisors. These are given by the condition on the curve that the curve breaks. Right, as two components, one of genus G minus I, the other one of genus I. Right, I need to take the closure of this. Another example are Britt-Netter cycles in general. Right, so this I actually intersect the interior of the moduli space. Right, so these are curves such that they admit GRD, a line bundle that gives you a map to PR, realizing the curve as something of degree D in that PR. And of course, yeah, so there are numerics here, right? So one needs the Britt-Netter number, for instance, to be -1, for this thing to give you a divisor and so on. And there are more. And they all play an incredibly important role in understanding the geometry of MG. Okay, so today, right, the example is F2D. So let me this is just notation, we will come back to this. Okay, so this is the moduli space of pairs, SH, where S is a K3 surface, and H is a primitive quasi-polarization of degree 2D. This is H squared. Yeah, what I mean here is, so polarization is what Robbie told you. So it's an ample divisor, it's an ample line bundle on S. A primitivity condition is not principal, it's primitive. This means that it's not a multiple of something, so in the sense of the natural numbers. And And quasi here, the word quasi, we can put it in between parentheses. I will allow my polarization to cease to be ample, but stay big and F. Okay? So I could actually keep the word polarization and allow S to have mild singularities, ADE singularities, and then okay. And so what is this notation? So we know that a K3 surface, so if this were to move in a family, right, the cohomology group stays constant. This is a topological invariant, right? So this lambda 2D is going to be H2 of the K3, and then the primitive one, the one that does not come from the projective space where H is sending my S to. So they're orthogonal to H. And then, so two K3s polarized are isomorphic, right? This comes with a Hodge structure, with a polarized Hodge structure, if these two structures are isometric as polarized Hodge structures, right? So then this space is the one that replaces, so the Siegel upper half plane for abelian varieties. This is the space of Hodge structures of K3 type that I can put on this fixed thing, and these are isometries. Okay. All right, and then what is so for these spaces, the most natural source of modular divisors are what are called Brill-Netter divisors. Let me stay with my notation. Okay. Sorry, not Brill-Netter, Nether-Lefschetz divisors. So NL divisors. So if SH in F2D is very general, the Picard group of S is generated by H. So I will look at the locus of polarized K3s or quasi-polarized K3s where the Picard rank is greater or equal than 2. Okay, this is of codimension 1 and is defined, is modular, is defined by a condition on the K3s that my moduli space is parameterized. And this is a countable union of divisors, and the question is how to index them, how to order them. And there are various ways. They come from two different worlds, the worlds of geometry and the world of modular forms. So Nether-Lefschetz and Heckner divisors. But essentially, let me just give you a bit of, so the indexing. So two flavors of these, which are essentially equivalent. So DHA. So these are going to be polarized K3s, for which there exists a class in peak not proportional to H, such that, so B squared and then B times H is this pair. So it's 2H. I want the genus of B, so it's an irreducible curve to BH and A. Okay? And of course, there are conditions on this H and A, right? So this, for instance, the Hodge index theorem that tells me that that a very general object here will have the two classes, H and beta, right? And the matrix spanned by this to have signature 1, 1. So the determinant of this matrix has to be negative. That's one condition. And in general, so this is a locus like this. It's not algebraic. I will define it as the reduced locus whose support is this. Okay, that's my divisor. And this is O. This is in general, so I'm defining it to be reduced, but it's not irreducible. So it's non-irreducible in general. Okay? And the second version of this is by looking at, so this space of K3 type Hodge structures on this fixed lattice, yeah, so on this fixed cohomology group. This is an open set inside a quadric, okay? And then there is a quotient So in this case, this is my O tilde plus, so this isometries. And then, so the second notion is the descent of hyperplanes. Here. Okay, and this is the notion of a Heegner divisor. And these two things coincide, so let me say maybe like this. So yeah, so maybe straight dV, this is, if I grab a V in lambda 2D tensor with Q, so it's the orthogonal intersected with this quadric, the descent, dV bar. Yeah? So this is the notion of a Heegner divisor. I will put in a second a bit more indexing here, but these two notions are equivalent. Yeah? So these divisors are the descent of hyperplane arrangements on this quadric. Okay? Yeah, maybe I should give an example here, a short example. So D1A, so this is the locus of K3s, so elliptically fiber K3s. So K3s that have, this is the class beta, that emit an elliptic vibration to a rational curve with some multi-section. And this, so yeah. Okay, and the main conjecture here is, so there is this conjecture, right now it's a theorem, so this is Maulik-Pandaripande from 2013. Is that the Picard group with rational coefficients of F to D. So this by the way, yeah, I mean, I'm defining here Weil divisors, right? These are codimension 1 up to rational equivalence. These are Q Cartier, all of them. So is that the you know, Q Cartier divisors up to rational equivalence, the Picard group of this moduli space is spanned by this divisor. So by NL divisors. And
why are there the Q Cartier, the variety factorial or something?
Yes. So it's locally, it's like MG. Locally you have a vector space quotient by a finite automorphisms. All the automorphisms that appear are finite. So is Q factorial, is more than that, it has finite quotient singularity. Okay, so let me use maybe this one. And yeah, so this was answered. This is answered a bit in a bit more general context. Actually, I mean, I could take the same for any lattice in principle. So I will take maybe I restrict myself to lattices that have signature 2, n, and I look at K3 type Hodge structures on them, quotient by isometries. So this question can be asked in that framework. And the answer is yes. So this is a theorem. So maybe, yeah, so theorem. This is Bergeron, Lee, Milson, Muglin, 2017. And then there is a small correction. Brunier, Suffetti from this year, is that so Maulik-Pandaripande conjecture holds. So any divisor actually is kind of remarkable, but any divisor is a Q linear combination of these modular divisors. Yeah? So these divisors that are defined by codimension 1 condition on the K3. And the very natural question now is what happened with effective divisors. So you could define, say, the NL cone as the cone of effective divisors generated by irreducible components of NL divisors. So irreducible components of NL divisors. Right, so this is generation as a cone. Okay, so this sits inside effective divisors in the Picard. And there are essentially three questions. I mean, so you ask, so the structure of the effective cone of a variety is very important. So I mean, almost never is polyhedral, but there is a very large collection where it is polyhedral. And not only that, in many cases also it breaks, it has a chamber decomposition, and each chamber, so there is one of these chambers is the ample cone, if I understand this, I understand projective embeddings, more or less. And then the other chambers are parameterized different by rational models of my variety. So I think, I mean, again, I don't think I have to stress this enough. This is an incredibly important invariant of a variety, the effective cone. And the questions here, so this is actually a question of Peterson. So he wrote this beautiful PhD thesis and then quit math, where I mean, the whole thesis is heuristics about what this should be and fundamental questions about these cones. So the first one is, is F NL finally generated, so polyhedral? The second one is, if it is, say it is or not. Yeah, I mean, we can just ask stuff. So can we compute this cone? Meaning, can we write down generators? Can we compute generators? And the third question is whether this, if there is an effective divisor that is not a positive linear combination of NL cycles, right? So what is the difference between these two cones? It's perhaps the hardest. So is there an effective divisor not of NL type and so maybe I should say a few words. So this question, this has been asked for some time with no positive answer. There is one result that is due to Voisin and Renstad, where they write down a divisor that physically is not supported on NL. So it's a codimension 1 subvariety that is not given by this condition. This is not in, I mean, it's in a sort of a broader moduli space, those of cubics. But this doesn't tell me anything about this class on the Picard, right? And that's the extent of our knowledge, so far, even in degree 2, okay, where the cone is generated by 2 rays. This was answered affirmatively by Brunier and Müller, 2019. So one is a yes. But the proof is very, very non-constructive. It shows that, so the proof goes as follows. It shows that there exists a class here, the Hodge class, so the class that one can write down with blind eyes. So you show that first, that is in the interior of the cone, and second, that these Nether-Lefschetz cycles, they accumulate to it as the invariants grow. Right? So this proof goes as follows. So you have a cone, you don't know if it's polyhedral or not. There is a class here, the Hodge class, and projectively, maybe like this, it's the Hodge class, yeah, the ray, and then projectively these DHAs, as the invariants grow, I need to index it in the Heegner side, but these are equivalent, they converge projectively here. Right, meaning if I take a small ball around here, there are finally many outside, and it's the convex whole of those. but so then the first theorem, our first theorem is answering yes to number 2. And actually we wrote, well, we is too many people, there is one among my collaborators that know how to code. And he coded a Sage program that you just throw in a lattice, right? And then it spits out the NL code. So in particular, you throw in, maybe I should say, so for the K3 world, this is a fixed thing, right? This is 2 copies of the hyperbolic lattice, so matrix 0, 1, 1, 0. 2 copies of the unimodular lattice of rank 8, so E8, minus 1. 2 copies, and then there is 1 extra copy that is spanned by one thing whose square is minus 2D. Okay? This is the K3 case. Yeah, so I wanted to, so when did I start? You, sorry. 20 more minutes, okay. Yeah, so maybe I should say one word about what goes in. I mean, so there is also a very long story, many attributions to give a sort of a canonical isomorphism between the Picard group of these varieties and a space of vector-valued modular forms. So this started with Borchers, who showed that there is a map, and then Brunier showed that it's injective, and the fact that it's surjective is this Bergeron-Lee-Milson-Moblin. So we translate the whole problem into a vector space of modular forms, where this lambda class actually coincides with an Eisenstein series that one can write down concretely. And showing this accumulation has to do with the fact that so Fourier expansions of Eisenstein series, the factors, grow much faster than those of cusp forms. Right? This is somehow sort of a classical story. The point is that in order to compute the cone, you need to make this explicit, right? And there are very few, I mean, there is a lot of literature about the growth of Fourier coefficients of modular forms, but very little of it is known for explicit ones. I mean, there is one classic one from Delin, but not much more, and these are vector-valued modular forms of half-integer weight. I mean, yeah, so we have to somehow find appropriate bounds, and then you can essentially compute. I mean, the problem is, so you have a given lattice, you give yourself a radius, you need to check that it's inside, and then to compute from which moment on they sit inside, right? And the ones before generate the cone. But so let me say, I want to say a few things about geometric applications. Geometric applications of the fact that we know how to compute this cone. So there are essentially 3. So first is the study of the NL positivity of the canonical class of these moduli spaces. So the relative position of the canonical class with respect to the cone, whether it's NL effective or not, how far away is it from it, right? So for instance, I mean, this is if I take NL, right? So the canonical class of a variety sitting in the interior of the effective cone tells me that the variety is of general type. The canonical class sitting outside the effective cone tells me the variety is uniruled, is covered by rational curves. So this is a very somehow, it tells me a lot of information about the geometry of the variety, and if it sits in the boundary, it tells me that it's of intermediate type. So then you go for studying fibrations, right? So this map my factor. Okay, so the second one is so we can obtain, due to this, unirulness results for moduli of hyperkählers, and I want to focus on this in my second half. And the third one is that we can also say something about the structure of families of hyperkähler varieties of low degree. So yeah, so let me briefly say what an hyperkähler variety is and why do we care. And the third question of this list, by the way, yeah, this I said this again. I mean, I said this. It's a question that at least I am very interested in, and yeah, no clue. And well, I don't think there is even an expectation somehow. Okay. So yeah, maybe definition. So hyperkähler varieties is a very natural generalization of K3 surfaces for higher dimension. So what I ask is to be simply connected. So let's say projective. Yeah? So it's a projective variety. So if this is trivial and it admits a two form, it admits a symplectic form. So h to 0 of x is generated by a single, wait. So this is a nowhere degenerate, so non-degenerate symplectic form, holomorphic two form. Okay? So I have a symplectic form on the tangent space everywhere. It's nowhere zero. Yeah, so they are important because of this fundamental classification theorem that tells you that any variety with trivial canonical class up to an étal cover can be written as a product of abelian varieties, hyperkähler varieties, and a third class. It's called Calabi-Yau varieties. And from the point of view of somehow written knowledge that there is a lot on the abelian side. The hyperkähler side is growing fast, but we still know very little, and the third class we know virtually zero. So yeah, the first question, I mean, these varieties were believed at some point to not exist in dimension higher than 2. There is literature to support that statement. And but yeah, Bouville came with an example in the 80s, 2 examples, right? So the first is you take a K3 and you look at subschemes of length n dimension 0, meaning points, n points on the K3, right? And when they come together, I need to add the rate in which they come together. So this is an example of these objects. The second one is what is called the generalized Kummer. So you take an abelian surface, you look at n plus 1 points on it, and then you sum them, you add them up. So this is an isotrivial fibration, and the fiber, so you can think of the fiber over 0 if you want, is again an hyperkähler variety. So this is called cum n of A, is the fiber over 0. And then there are 2 other, so this, you see this comes, for any n there is 1, right? And then there is 2 sporadic examples, one in dimension 6 and one in dimension 10, due to O'Grady. Okay, so like 10 more minutes, something like this, right? Okay, so maybe one classical. So I mean, after having existence, so maybe I should say, so these ones, right? So you grab a K3, you look at the Hilbert scheme of points on it, and then because the K3 moves in a 19-dimensional family, this gives me a 19-dimensional family, right? But the moduli space is 20-dimensional. So if I just look at the formations, it gives me a 20-dimensional local neighborhood. So this has 20 moduli. This one has 4, and abelian surfaces moving a three-dimensional family. Yeah? For moduli. And then this one has 5 moduli, and this has 21 moduli. And then the obvious question is, can we write down one? Can we write down a general one? Right? Can we write down a general hyperkähler, say of this or this type? And yeah, so the first example is Bovil-Donaghy from the 80s, where they say, look at, so yeah, we will look at a cubic fourfolds. So in P5, cubics. Yeah. So this goes to the moduli of K3 fourfolds, yeah, of degree 6. So also, I mean, this has 2 components, and it's one of them. So one is called split, the other one is called non-split. Okay. And I grab a cubic, and I look at its lines. Right? So lines in the cubic, they have a natural fourfold structure, algebraic variety structure, and this also comes with a polarization induced from the O1 here. That is of degree 6. So if you count here, this is surjective, well, it's dominant. Yeah? This is dominant. So this construction gives me a very general hyperkähler fourfold of K3 type, degree 6. Yeah, one of the components. And this has been generalized, but essentially all the examples we have are for K3 type. And this has been a question that has been somehow bothering people for quite some years. In particular, this example, this is from the 80s, this is fairly old. Can we write down the equations, or can we describe the general element in the moduli space here, say generalized Kumers of dimension 4. And there is no single somehow written down example. We can only describe families of codimension 1 and 2 and higher. So, so there are, yeah, the list of examples here is, I mean, there are 4 more essentially. The Barboisan, LLSV, and yeah, there is one of Macri, Laos, and yeah, it's a long list of people. But anyway, there are few examples, all landing on the K3 side. So the motivation here is, so being able to write down equations or to describe the general element in moduli is not the same, but is very closely related because of the way the human brain works to the space being uni-rational, to being dominated by a rational variety, right? Because essentially, you know, so in this case, right, this is a projective space, right? This is uni-rational, and it's because you know, descriptions have to do with choices, so you choose things, and then managing equations relating these choices is simply too difficult. But so if the things you choose move freely, in this case the coefficients of my degree 3 polynomial, right, then I get the very general element. All the constructions we have induce also a unirational parametrization. And yeah, we obtain uni-Rulner's result, which is weaker for this case, this mysterious case, and also this mysterious case. So maybe, yeah, so theorem 2. Is so for so moduli of OG6 degree 2D and moduli of generalized Kumers of dimension 2n and degree 2 only. We can do the first case. So for small n and d, the canonical class is not a pseudo-effective. In particular, the space M is uniruled. In these cases, for this small n and d. And yeah, so how do you, okay, or maybe I have 7 more minutes, it's okay. Right, so, and I can say one thing about this third application, which is really about, so this has potential to be exploited further than this. This is a bit done. We exploited everything you can do, and the way the proof here works is that you find in the Picard, you find an hyperplane where the NL cone is on one side, and you have an ample class here, and the hyperplane is given by intersection of a very positive curve, and you show that the canonical class sits on the other side. Okay, so the canonical class intersects a very positive curve, in particular an F curve, a curve that covers my thing, negatively, meaning it cannot be pseudo-effective. And this implies uniruleness. So, yeah. And how to compute the intersection product is actually kind of cool, because you need to go again to the space of modular forms. And the intersection product of the canonical class with a curve, you can read it off from Fourier coefficients of modular forms. So it looks like a multiple, the canonical class is the dimension, in this case 19 times lambda, minus, and there is a little chunk here, so this is so it's the dual of the space of modular forms, so I will put here 1 divided by 4, and then the function, taking a modular form and gives you a rational number, induced by extracting the -1, 0 Fourier coefficient of this modular form, minus something else, which is okay, is controlled. I mean, I intersect this and I show that it's negative, so then the rest is, yeah. And then the lambda class corresponds to because again, the isomorphism is with the dual, so it corresponds to sending the Eisenstein series to -1 and the space of Kasparov to 0. So that's how it looks in terms of functionals. So you see that if you have, yeah, okay. So
When you have a result like that, does it tell you that you can write down an example or something?
yes, you can compute it. I mean, yeah. So the result. So the whole framework tells you actually, because the curve we take is lambda to the power dimension -1. There is essentially one known ample class in all these moduli spaces, and this is the Hodge class. And we know nothing about the ample cone, yeah? But if my curve is lambda to the, in this case, 18, okay, or dimension -1, so this is a very positive curve, very, very positive. So actually the expectation is that, I mean, one should be able to choose a better curve and get more uniruleness results. Here you get the worst you can get because you take the most positive curve there is. Yeah? An ample class self-product 18 times. So then so yeah, I don't know if, I did not tell you, okay, let me write it down. So there is a relation between this M and mu and the H and A, which is concrete, okay? So this you can think of as a NL divisor for some numerics. And then the intersection of this with lambda to the 18 is a constant multiple of taking the -m mu Fourier coefficient of the Eisenstein series. And these Eisenstein series, you can write them down. There are computers that give you arbitrarily large Fourier coefficients. So it's just writing this in terms of these objects. And then you compute the numbers. Yeah, I don't know if this answers. But yeah, let me say one word about the last application, which is a very, I think it's a cool question. It started with a paper of Borges, Shepard Baron, Pantev, and Katsarov, 98, is in Jack. They ask if I have a family, so the question, so I have a family, say of polarized K3s of degree D. So the question is, if pi is not isotrivial, can be projective. So essentially, can I have a complete sort of subvariety in the moduli of polarized K3s? So polarized. So I took out quasi. If I put the word quasi, this becomes a bit of a trivial question. And they say no, so the theorem is no if the degree of the K3 is 2, and then there is a result of the Bar-Macri from 22 that says yes for can be projective question mark. Yes for D. I think D is greater or equal than 62 and some other cases. Something like this, don't remember. But anyway, that doesn't matter. So it's a low degree phenomenon that you cannot have complete curves in moduli. And having complete, maybe my last minute, it says that, so if you look at the quasi-polarized locus, the locus where the polarization becomes a quasi-polarization, this is a divisor. And if I show that this divisor is ample, it means that every curve has to intersect. So it has to do with understanding this divisor, the position of this divisor in the NL cone. This is an NL divisor, concrete, you can compute it. Yeah, so we show for the first case of the generalized Kummer, for which, again, we know very little about the geometry of the general one. So theorem maybe, so theorem 3 is, so the answer is no for, of the same question, for a family of cum2 type, degree 2. And this is simply because the NL cone is spanned by a single ray, the lambda class. So, but yeah, so knowing more, okay, I stop here, I'm sorry, yeah. I will stop here, yeah. Yeah.
So, since you know this effective divisor, in principle, you also know all the networks. Well,
yeah.
use that to optimize your, find the curve that is the most, the least net that.
Yeah, this is a good question. I think it's, I mean, understanding the net cone, yeah, no, we haven't used it, yeah, but also because I don't know if I walk around the cone, I also cannot say anything about, which ones are more positive than other ones. Well, it's kind of a translation of problem to my mind, So you are saying, okay, I go to the net cone of curves, and I would like something that is still net, but the least positive one, right? So this is, if you are going to use your duality, it kind of has to do with, walking around the effective cone and look at those, that are somehow the least positive ones as well, right? And yeah, so my question is no, but I think, I mean, these are sort of like kind of immediate applications. You use very little about the structure of the cone itself. It's just, hyperplane sits there, and the other one is that is one-dimensional, the effective cone. So that gives you this result. So, I think, yeah, I think there is space there. I think, so in order to have more, you need to understand ample classes also. We only know the lambda class. So to know a little bit of a range around lambda, you are still ample.
So what is the
This?
No, the video two.
Yeah, is because the group is not O tilde plus. It's so you know the moduli space. These Hodge symmetries I was lying a little bit, but what you need to caution by is what's called the monodromy group. Meaning if you go around one is the group that acts on H2, right? And if this group is O plus tilde, then you win. Then you can use this whole machinery. Also, this isomorphism between Picard and modular forms work only on that setting. For the generalized Kummer, this group is not if the degree is higher, is neither contained nor contains. It's something, yeah. So yeah, you are missing the whole translation. I mean, we work in the modular form side, right? And you miss the translation from start. So yeah. Yeah. That was a cut. Sí. Me voy a ir a sentar ya. No.
entonces no es posible usar ambas las cosas. O sea, proyectar, pero también escribir. No es posible. Sí. Bueno, no hay problema. So it's not possible because it's not possible to actually use both the blackboard and. I mean, I guess it's okay. It's okay. It's okay. It's okay.
Maybe by the end we can lift it and
Yeah. All right. Okay. I don't think. Yeah. Eu baixei agora.
we will be talking about matrix
Yeah, so thank you very much for the invitation to speak. I'm happy to be here in Chile for the first time. So the last two talks that we saw were about the global geometry of algebraic varieties, and what I'm going to talk about is going to be essentially in a purely local setting, and is hopefully going to involve some interesting combinatorics. And hopefully by the end of the talk, it'll be clear why matroids and semirings have to do with what they have to do with curve singularities. Okay, so so by way of motivation, often we get a lot of information out of studying spaces of holomorphic maps into a variety X. Today, for everything that I'm going to be saying, X is just going to be a projective space. So if you fix a degree, those linearly non-degenerate morphisms from P1 to Pn of degree d, the parameter space of those morphisms is essentially an open subset of a Grassmannian, because every such morphism is just given by a collection of n+1 linearly independent homogeneous polynomials on P1 of degree d. So in a sense, the space of degree d morphisms from P1 to Pn is not very interesting. Again, it's an open subset. You can think of it sort of as an open subset of a Grassmannian, but things become a little bit more interesting when I consider something a little bit more refined, where we impose that the images of our morphisms have fixed arithmetic genus. So those subvarieties I'm going to label as MNDG, and sort of by analogy with what happens in the case where the ambient dimension is 2, I'm going to call these parameter spaces Savary varieties. And we can ask very basic questions about these parameter spaces, starting with whether or not they are irreducible as topological spaces. The point being that in the case of plane curves, n equals 2, the Savary variety is always irreducible, and that is a consequence of Joe Harris's work from the 1980s. In particular, what we know in the case of ambient dimension 2 is that the Savary variety is the closure of the locus of morphisms whose images have exactly G simple double points, which I'll refer to as the G nodal locus. So you might wonder whether that situation persists when the ambient dimension goes up, but it doesn't in general, and I'll try to give you some reasons why. And the techniques that I'm going to use are going to be very naive and crude, but basically everything is going to be predicated on dimension counting So actually, I'm going to single out inside of each of these parameter spaces M and DG maps whose images have a single very bad singularity of arithmetic genus G, or delta invariant G, a fixed value semigroup, which is some arithmetic data attached to the singularity that that'll define in a second. Okay, so what's a value semigroup of a singularity? In the simplest case, our singularity is a unibranch singularity, or in other words, you can think of it as a cusp. And locally, you can parameterize your cusp by power series in some local coordinate. And a local parameterization by power series is just dual to a ring map, where the domain, actually, how do I get a red? Oh, there it is. Yeah, so this ring in the domain corresponds to the target space, and then of course the range is power series in T, and what's nice about power series in T is that there's a natural non-Archimedean valuation, just given by order of vanishing of power series in T equals 0. So then, what's this value semigroup? It's the image of the composition of the ring map that locally describes the singularity, together with the T-adic valuation. And when we compose, the composition lands inside of the natural numbers. It's a semigroup because when we multiply two power series, the orders of vanishing in T equals 0 are additive. Actually, it also has finite complement. And in fact, the number of elements in the complement, I think I'll see this in a slide in a second, the number of elements in the complement is exactly the delta invariant of the singularity. So informally, you can think of this procedure of passing from the local algebra of the singularity to its value semigroup as taking a logarithm. And then this story works more generally. If now we have an arbitrary number R of branches, then our singularity is specified by a ring map, where now the target is a product of one-dimensional power series rings. And then the value semigroup, again, is just the image of this ring map composed with the product of adic valuations on each of these factors. Okay, so somehow the philosophy here is that the topology of this parameter space of morphisms from P1 to Pn with fixed numerical data attached is controlled by this arithmetic object that's the value semigroup. And in particular, we're going to count dimensions using arithmetic properties of the value semigroup. So how is that going to work? So the idea is very simple. If we require our morphisms to contain, if we require images of our morphisms to contain singularities of a given type, well, that has to impose algebraic conditions on the coefficients of our morphisms. Okay, so that's one point. The other is, because I mentioned that we were interested in determining whether this parameter space MNDG is irreducible or not. And I mentioned in the case when n equals 2 that it's exactly the closure of the G-nodal locus. So one important consideration to keep in mind is that in general, this G-nodal sublocus of the Serre variety is always going to be of codimension n-2 times G. And the reason is quite simple, or elementary rather. So the idea is that if you fix the target and the two preimages of a given node, then you can work out that that imposes exactly 2n linearly independent conditions on coefficients. And then when you vary the target and the two preimages, you cut down by n minus 2 conditions. So then you end up with n minus 2 algebraically independent conditions, and then you have to check that those conditions are in fact independent across distinct nodes. But it should be credible, at least, I think. Okay, so if we wanted to check that this parameter space MNDG were irreducible, its codimension would have to be at least, its dimension would have to be less than or equal to the dimension of the G-nodal sublocus. Because that's the only way that it could be contained in the closure of that G-nodal locus. But that's just not going to be true in general. And when that's not true, we're going to say that this space is excess dimensional, and as a result, it's going to be reducible. Because there will always be an extra component besides the G-nodal locus, besides the closure of the G-nodal locus. Okay, so I want to spend a little bit of time talking about how dimension counting works in the unibranch case, before hopefully saying a little something about the more general situation at the end. So if we fix a particular type of cusp, then it's going to be interesting to distinguish between two basic types of algebraic conditions imposed by the cusp. And there's a set of very simple conditions that I'll refer to as ramification conditions. And those are just defined by, so if we specify the orders of vanishing of the local sections that in the preimage of the cusp, then the idea is that fixing the ramification data just amounts to imposing a certain number of linearly independent vanishings of derivatives. And that number of conditions is completely predictable. It's just given by the discrepancy between the order of vanishing of local sections in the preimage of the cusp and sort of the generic vanishing orders from 0 to n. So in particular, what we can do is we can distinguish ramification profiles in the preimages or cusps, and then we can further refine these spaces of these very varieties where we fix the data of the value semigroup of a cusp according to the ramification profiles. And if we do that, then we get some kind of generalization of a Schubert subvariety of a Grassmannian. Okay, but the really interesting conditions that are more subtle are what are, just for lack of a better terminology, I'm going to refer to as conditions beyond ramification. And those, they come from particular features of the additive structure of the value semigroup, or if you like, from the multiplicative structure of the local algebra of the cusp. So at this stage, I want to give a feel for at least the sorts of questions that I'm interested in answering here. So one natural goal would be to produce a combinatorial model that at least conjecturally accounts for all of these conditions beyond ramification. And I'm not sure that I'm going to give a complete detailed answer. We have some kind of conjecture about this. I'll try to give a feel for some of the ingredients that go into it. A second sort of orthogonal goal would be to produce upper bounds on the genus of what I'll call a generic cusp. So a generic cusp would mean the genus, the genus of a cusp for which we impose a given ramification profile, but then just assume that all of the higher order coefficients are generic, that there are no algebraic conditions being imposed on higher order coefficients. The point being that, again, you don't really know, if we simply fix the ramification profile, we have no idea what the actual delta invariant of the corresponding singularity will be. So this involves some, we have to produce some estimates in this case in order to conclude anything about excess dimensionality or reducibility. Okay, so as far as a combinatorial model goes, in order to give you a feel for the ingredients, I have to tell you a little bit more about the combinatorics of value semigroups. So in the case where our singularity is a cusp, I mentioned before that the value semigroup has finite complement, and that the number of elements in its complement is exactly the genus, or the delta invariant of the singularity. And because that semigroup has finite complement, it's actually determined by its restriction to the numbers between the positive integers between 1 and 2g. That's just sort of a basic combinatorial exercise. So because S is determined by this intersection, we can codify it as a lattice path that starts in the origin in n squared and ends in g comma g, where at each stage I'm going to go up either 1 unit or to the right by 1 unit. And I'll go to the right every time a number between 1 and 2g belongs to the semigroup, and I'll go up every time it belongs to the complement. And I'll give a concrete example in a second. In this picture, it's going to turn out that ramification conditions are naturally encoded as boxes under our lattice path, and that conditions beyond ramification show up as collections of boxes above the path. So to be concrete, let's assume that n is equal to 4, g is equal to 7, and then I actually need to assume that the degree of my morphisms is a lot bigger than the arithmetic genus. It's just some large number. And let's assume that the value semigroup is generated by 2 and 15, which fits into this broader class of what are called hyperelliptic examples. That always generate. So hyperelliptic just means that 2 belongs to the semigroup, but as soon as the genus of the semigroup is G, it's necessarily of this form, minimally generated by 2 and 2G plus 1. So the space of morphisms of degree D from P1 to P4, with whose unique cusp has this particular value semigroup, the corresponding maps will have various possible ramification profiles in the preimage of the cusp. But one generic possibility would just be to assume that the local non-zero vanishing orders in the preimage of the cusp are 2, 4, 6, and 8, or in other words, the smallest successive even numbers. I mean, these vanishing orders, they have to be elements of the value semigroup, necessarily. And so when I say generic possibility, these are just the lowest possible numbers that I can choose. Okay, so graphically, how do I represent the semigroup and sort of the ramification data and hopefully the conditions beyond ramification? Well, in this picture, I've singled out this lattice path that starts at 0, 0 and ends at 7, 7. And this describes the semigroup. Now, you should think, what you should keep in mind is that each of these first 4 columns is supposed to correspond to, the indexing just corresponds to the way that I've indexed the local parameterizing functions of my singularity, or equivalently, these are going to be, essentially these correspond to sections of my morphism that don't vanish in the preimage of the cusp. And so then the idea is that these boxes that appear under the path in gray, these codify ramification conditions. And the reason why is that, if you think about it, the set of boxes underneath each of these horizontal segments indexed by 2, 4, 6, and 8, this is exactly this number, ai minus I, that appeared before. And again, these conditions are sort of linearly independent vanishings of derivatives. So those are the ramification conditions. But then what's more subtle are these conditions in red. And for each of these three columns, column 2, 3, and 4, what I claim is that each one of these boxes indexes an algebraically independent condition beyond ramification. So how should you think of these conditions? Well, let's single out this very first box that appears. The point is that, so how do you think about the condition that's indexed by this box? When you normalize these local sections in such a way that the leading coefficients are just 1 every time, so according to this convention, according to this ramification profile that I've chosen, f1 squared and f2 would both have valuation 4, and they would cancel, there would be cancellation of initial terms when I compute their difference. So generically, if there were no algebraic conditions being imposed, you would expect that the vanishing order in t equals 0 of this difference be exactly 1 more than the valuation of f2, or in other words, it would just be 5. But the point is that 5 is not authorized because 5 doesn't belong to the value semigroup. So the only possible conclusion is that there's an algebraic condition, namely that the initial term, that the initial coefficient of this difference be equal to 0. And then the idea is that the first box in column 3 and the first box in column 4 behave similarly. In column 3, this one would be associated to f1 cubed minus f3, whereas in column 4, this one would be f1 associated with f1 to the 4th minus f4. And then there's some kind of inductive, so those are those conditions. Again, they correspond to these first boxes in each of these 3 columns. And then there's some kind of inductive promotion procedure that allows me to walk up each one of these 3 columns inductively, building algebraically independent conditions at each stage. And it's completely elementary and straightforward, but a little bit messy to write down, so I won't write it down explicitly. But the idea then is that you walk up each column, and what I claim is that you get an algebraically independent condition at each step, and that accounts for all, actually counts for all algebraically independent conditions beyond ramification. And we proved that, so actually, if you notice again in this picture, so what's sort of the numerology that you should take away from this picture? The point is that the total number of colored boxes is n minus 1 times g plus 1. And that turns out to be typical. In particular, if you subtract 1, you get n minus 1 times g. Subtracting 1 amounts to allowing the preimage of the cusp to vary. So the conclusion, which is sort of more general, is that in this case where the value semigroup is of hyperelliptic type, then assuming the degree of the morphisms is large enough, the codimension of the space of morphisms with hyperelliptic cusps is always going to be n minus 1 times g. And then we further speculate that as soon as you fix a ramification profile inside of this severity type variety, the corresponding subvariety is actually irreducible and unirational. So how much time do I have at this stage? 15 minutes? Okay, so I think rather than, okay, so then we have some kind of conjectural picture for how this dimension counting should work in the case of a cusp in general. I don't want to belabor this at all, but what are sort of the ingredients that go into this dimension counting? There's some arithmetic functions attached to the semigroup. So one arithmetic function that's important is for a given element of the semigroup, the number of elements in the complement that are strictly larger than it. That's this function rho of S. And then another sort of more important ingredient is what I'm going to call Betty elements. And these are sort of elements that have qualitatively distinct factorizations with respect to the elements of a given ramification profile and the minimal generators of our semigroup. There's a way to make that precise. I'm not going to go into it. Well, actually, maybe I should say just a word about it. So the idea is that if you single out a given element of the semigroup, and you ask how it factors as a non-negative linear combination of elements of the ramification profile and minimal generators, then the idea is that you can stratify the space of factorizations into equivalence classes, where you decree that two factorizations, thought of as two vectors, integer entry vectors, are equivalent if and only if you can link them by a chain of vectors, of factorization vectors, for which at every stage, the dot product of successive factorizations is non-zero. And then a Betty element formally turns out to be an element for which there are at least two distinct factorization equivalence classes. So I gave an example here. In the case where the semigroup is minimally generated by 4, 10, and 15, and you single out, this amounts to sort of a generic, I think, ramification profile. In this instance, the Betty elements are 8, 12, and 20, and I've sort of singled out these qualitatively distinct factorizations as non-negative linear combinations of these elements 4, 8, 10, 12, and 15. So conjecturally, we expect that in general the codimension is polynomial in, first of all, the ramification conditions, which are this minus 1. Psi of S is the number of distinct factorizations. Rho of S is this arithmetic function that counts number of elements in the complement strictly greater than an element. And then the sum is over Betty elements, whose role is exactly to single out which columns, in which columns of our diagram conditions beyond ramification actually appear. So, and then there's some kind of corrections that are finer, but I won't get into those here. Yeah, and then, okay, so, and then we have some results about, so in the hyperelliptic case, the codimension was never strictly, obviously it was always greater than n minus 2g. To produce examples where the codimension is strictly less than n minus 2g, we actually studied generic cusps whose ramification profiles were sequences of, were arithmetic sequences of successive even numbers. And we had to produce estimates on the genus of the corresponding generic semigroups. Okay, but to finish, I would like to say just a couple of words about what happens in situations where the singularities have multiple branches. And there's a particularly nice class of examples which are multiple points, where each of the branches is smooth. So in this setting, what we'd like to do is sort of two things. We'd like to count algebraically independent conditions imposed by these multiple point singularities, and we'd like to produce upper bounds on their genera, because we don't know what they are a priori. Okay, so more specifically, I'm going to impose that I have R branches, and that the resulting singularity have embedding dimension L. And what's nice about this particular class of examples is that counting conditions imposed by the singularity is actually easy, because generalizing sort of this heuristic that we did for simple double points in the beginning, you can check that requiring R branches to be incident at a point imposes R minus 1 times n minus R conditions. This generalizes the case of the simple double point. And then the condition on the embedding dimension, this is just a determinant. Well, actually, I should say that there are at least this many conditions. At most this many conditions. I think that's what I want. This is just some. These are determinantal conditions, right? So counting conditions is easy. It's not clear, though, a priori how to compute the genus or the delta invariant of one of these multiple point singularities. There is one situation, though, where computing the genus is also easy, and that's the case where the multiple point is locally planar. And the reason, at least this is morally, it's not, I don't think this is a rigorous, I'm not sure how to make this into a rigorous argument, but morally, what you should think is that in the locally planar situation, so you should think about, first of all, a multiple point is analytically just equivalent to a line arrangement. So you have an essential line arrangement, you have a certain number of lines that intersect in a single point, and if that line arrangement is just inside of A2 or C2, you can deform these lines in such a way that the arrangement becomes generic. So two lines just intersect two at a time. And in that case, the genus is just the number of double points in the line arrangement, so it's just a binomial coefficient. We can actually prove that rigorously, though, using the combinatorics of semigroups. So then the key calculation is that whenever R is big, the total number of conditions is strictly less than n minus 2 times this genus, and therefore the corresponding severity varieties are excess dimensional. Okay, so the very last thing I'm going to say is something about what we can do beyond the locally planar multiple points. So the idea is that, first of all, instead of thinking about the value semigroup that's contained inside of n to the r, you should really add infinities, and you should compactify it by looking inside of n union infinity to the r. A priori, that sounds sort of stupid, but the idea is that as soon as you do that, you can make sense of what it means for elements to have a support, because support here is just going to mean elements components entries that are not equal to infinity. So it turns out that the value semi-ring inside of n bar to the r is always minimally generated by elements of minimal support, or in other words, elements that have a minimal number of entries equal to infinity. And that turns out to be a reflection of some deeper property, namely that, so this value semigroup is the image under a semi-ring homomorphism of what I'm going to call the tropical support semi-ring associated with the singularity, which you should think of as an infinite matroid. So I think I have very little time at this stage, but what's a matroid? It's some kind of abstract generalization of a vector space. There are many different cryptomorphic ways of specifying a matroid, but one of them is in terms of a finite ground set, and then a set of minimal dependent subsets, in other words, the circuits, that satisfy some kind of circuit elimination axiom. So it turns out that the value semi-ring can be thought of as an infinite matroid where you just relax the condition that the ground set be finite. It can now be infinite. And then modulo some genericity hypotheses, you can explicitly determine these generators of minimal support. So what we proved is essentially an algorithmic description. It's an explicit combinatorial description of the value semigroup attached to an essential line arrangement, or in other words, a multiple point with R branches and fixed embedding dimension n. It's spelled out in terms of, so we have an explicit description of its conductor, which just means the smallest entry for which every vector whose entries are greater or equal to these entries appears inside the value semigroup. And in each particular case, you can work out exactly, so in order to determine the genus of the value semigroup, you need to work out those elements that are strictly less than the conductor. And this theorem gives you an algorithmic prescription for doing that. Unfortunately, it's sort of only very numerologically explicit when the embedding dimension is 2, and the combinatorics becomes more subtle as soon as n is at least 3. Sorry, I guess I'm probably out of time. 5 minutes? Okay, so maybe just the very last thing I'm going to say, I want to say a word or two about this tropical support semi-ring. So what do I mean by that? So remember that, that our multiple point is going to be locally parameterized by a ring map whose target is a product of power series rings. So, so this support semi-ring is just going to be essentially generated by the monomials inside of this product of power series rings that appear in some parameterization, in a parameterization of my singularity. Yeah, so one way of specifying a matroid traditionally is in terms of cycles. Actually, probably I should have stuck to circuits. A circuit is going to be a minimal cycle. But then the idea is that you can view, so if you take as the ground set the set of monomials inside this product of power series rings, then cycles are going to be exactly monomials that appear in the local algebra of the singularity, and circuits are going to be minimal supports, and these are going to generate the support semi-ring. It's an infinite matroid because the set E of monomials is infinite, but then the value semi-ring is a homomorphic image of this infinite matroid. So I think I will stop there. Yeah, I don't know. Yeah, of course you could ask that kind of question. I don't know. That's a natural question to ask. Yeah, because there's just no more than one. But.